Dear gentlemen, dear ladies and gentlemen from the auditorium, it's again our session about wide bandgap expert talk, and I'm happy to have you all here at my desk, and we are ready to start. The first question is coming. So we are ready to start. What's the SMPD package?
Yep.
It's addressed to Littelfuse.
Yeah. Hi. Hello, everyone. Hello, Mr. Bodo. Thank you for the opportunity.
Hi,
and I would like to explain about the first question. What is SMPD package? So SMPD stands for a surface mount power device as a long form. And it is an advanced top test site cooled electrically isolated package, which was pioneered by IXIS, then Littelfuse, then IXIS, now Littelfuse, back into the year 2008. And it looks something like this. You know, it's on my finger, like just my fingertip. And this is basically a phase leg of SMPD to MOSFETs or chips inside. The thing is, SMPD is kind of a platform, so it can be integrated with the variety of technologies like silicon carbide MOSFETs, IGBTs, diodes, thyristor, track, and so on. It is available from voltage class from 40 volts to 3 kilovolt. There's such a wide range, and also available with different topologies like single switch, co-pack diode, buck, boost, rectifier, and so on.
So I think it's something for volume production, may addressing white goods. Any questions between the speakers?
I've got a question. Aalok, this is a fully insulated package, right? The footprint,
yes.
is this matching a D2 pack, or is this slightly larger? Or...
No, it is larger than D2 pack for sure. So if you see the footprint wise, or if you see the area of this particular copper plate, it is 23 by 25 millimeter. So it's like in that dimension.
Okay, thanks.
Yeah, no worries. Thanks.
So it has the capability to probably include a microinverter.
Well, depends on the chip size for sure. But I would say for microinverter, like if you have like very big chip size or something, maybe difficult, but definitely it goes with like phase leg. What we offer rectifier bridges. We offer buck boost integrated, like so diode chips inside, MOSFET chip inside, co-packs, IGBT, and so on.
Okay. Thank you, Aalok. That's a question addressed to Navitas. GenSiC offers a very wide range of voltage classes. Where do you see the largest growth?
Sure. Okay, so for the people who are not aware of GenSiC and Navitas, Navitas is a GaN company, and it acquired GenSiC, which is a silicon carbide company, about a year ago. So GenSiC offers a wide range of voltage classes, the broadest in the industry, from 650 volts to 6,500 volts. Now, from a marketing point of view, the lion's share goes in 1,200 volts. And we see that mainly industrial for higher power, but also we see the growing market in EV traction, like most people, from the EV, the battery voltage going from 400 volts to 800 volts, that's requiring 1,200 volt devices. So obviously, we see the large growth in EV for the traction, for the OBC. We see emerging, I'd say emerging, but growing other voltage classes, 750 volts, obviously for EV traction, for the 400 volt bus, and 650 volts for OBCs, DC to DC. One thing with GeneSiC, we do the higher voltage capability. So 3.3 is something very interesting right now. That's a very, I'd say, high growth market for medical, industrial applications which need higher bus voltages. 6.5 is more for medical and for traction, locomotive and heavy duty. And we offer die, we work with module partners to support that. Another voltage class we see, which is up and coming, is 2.2 kV or 2 kV for solar applications, where we're seeing bus voltages rise to like 1,000 volts or 1,500 volt buses.
Thank you, Llew. Any questions, comments? Otherwise, let's go to the next question. And the next question is coming up.
Hi.
It's addressed to Rohm. Are you proposing to use transfer molded modules to address this architecture proposal? What would you say are the main advantages of this choice when comparing it with a discrete or traditional GaL-based module?
Hi. Yes, I'm Carlos Fuentes from Rohm Semiconductor. Hello, everyone. Thank you for
Hey, Carlos.
For the opportunity to be here. Yes, thank you for the question. We see that these transfer molded modules present several advantages. For example, I mean, the ones that we're proposing in the article are 6-in-1, 4-in-1, and there's also the DOT, which is 2-in-1. And with these transfer molded modules, because of the size they have, they reduce the overall footprint. We can put 6 devices in one and significantly reduce the space in the PCB. Also, they simplify the cooling because these transfer molded modules can be cooled down with a single smaller heatsink instead of let's say 6 discrete devices connected to the same heatsink. And also, you don't need to consider the creepage for every single device because you have the 6 devices in this one transfer molded package, and then that further helps you reduce the footprint and simplify your assembly. Finally, also regarding the assembly itself, there's only 2 screws that are necessary, and the devices are isolated themselves, so you don't need to put an additional isolation sheet in between. So overall, it's a much simpler, more neat way, compact to implement your design. In the article, we go along also to explain how the different topologies inside our residential setup that we have proposed could be implemented just using these devices.
Thank you, Carlos. Any additional questions from the auditorium?
Carlos, are these automotive or industrial, or are these bottom cycle, top cycle, dual side? What's the deal?
It's top side cooled, yeah, it's only one side, and they are directed to. I mean, we have the plans to release them for also a G324 to automotive applications, but initially the goal is to offer them for PV applications, industrial applications in general, so data centers or UPS and so on. We have them in 1200 volts and 750. So, and with most current million values that we offer in the current 4th generation of silicon carbide devices.
Okay, thank you. The next question is addressed to Littelfuse. Is SMPD available for 1200 volt SiC device? If yes, what's the minimum RDS on available?
Yeah, so SMPDs are available in 1200 volt silicon carbide. So there are different generations available. So at the moment, under development is our 18 milliohm generation, which is the lowest RDS on SiC MOSFET in phase-leg configuration in SMPD.
Thank you, Aalok. So the next question is coming up. The latest, it's addressed to Navitas. The latest Llew System Plus SiC transistor comparison report shows GaN-SiC MOSFETs with the best figure of merit of all 12 SiC MOSFETs and even outperform trench. How is this achieved? So that's to Llew.
Right. So yeah, so GaN-SiC has, so if you know MOSFET technology, you've got both a planar gate right now and you've got a trench gate. There's a couple of guys who offer the trench, there's one on the call today. And the majority offer planar because it's still a, silicon carbide, still a, a growing adolescent technology, and there's still processing challenges, and especially with trench. So what GaN-SiC has done, it's offered this. It's a kind of a hybrid of the two. It's still a planar gate structure. However, we have something proprietary involved in the cell unit design, which is called trench-assisted planar gate. And what this does, it offers the highest performance, the highest figure of merit compared to all the competing solutions in the market. And this was performed by Llew Development System Plus, where they analyzed, I think they've done the report, the last report with 35 MOSFETs, and they tested them, and it shows GaN-SiC to be the highest figure of merit against all the competition versus trench also. So we do that with like I said, with the trench-assisted planar gate, and you can go on our website and look at that in more detail. Yeah, it offers very fast switching. It also offers a very low temperature versus RDS on shift. So when you look at your data sheet at 25 degrees, there's one thing with silicon carbide, you should look at your data sheet at room temp, but also at hot. And then you can determine really when you're testing in a real life application, realistically what that RDS on should be. So you can see GaN-SiC with the lowest shift over temperature. Okay.
Thank you, Llew. Any additional questions at that point?
Yes. Yes, for me, one question, the Llew data is included, the measurements made by Llew are until what point in time in the report? The figure.
So they do two figure of merits. They do RDS on versus, area size. So you could say RSP, and then they do QG versus RDS on. So the other figure of merit. So those are two data points they use. I think it's at room temperature. I did ask them if they should redo it at hot, but it's I think with this report it's at room.
My question is it still data from 2021, right?
But the last report was December 2021, right?
Yeah, okay. I was just wondering. And the thing is, our fourth generation came around that time, so I guess the data is not included in that report then.
Yeah, sure. Yeah, since then maybe there's been more releases of different technologies. Yeah, sure.
Thank you.
Thank you, gentlemen. We can continue to the next question. So the question is addressed to Rohm. What do you think this converter architecture is beneficial on a system level?
Okay, yeah, that's probably related to the article. So, well, it's no surprise for anyone that due to the current decarbonization trends and the increase in energy costs, efficiency is a high figure of merit for everyone, especially in the residential sector, where we try to keep the costs low. And in that sense, we see that a unified DC link approach for the connection of multiple converters will decrease the conversion steps. So nowadays, what we do is we produce energy from the PV panels to the grid, and then sometimes we connect an energy storage system directly to the DC link, or sometimes to the AC side. But the car always goes to the AC side. I mean, either by an AC wall box or a DC wall box. In any case, it will be connected first to the AC side. So in order to do conversion steps, we need to go to AC before we go again to DC. So in that sense, if we use a unified DC bus in the house and a DC wall plug for charging the car, we reduce the amount of conversion steps. And we see that as a low-hanging fruit for upcoming residential trends in the upcoming years. So that's why we believe this approach, because there's no developments involved, will have a positive impact and will be implemented in residential settings in the coming years.
Okay. My question is, if we have DC links for charging cars, what will be the voltage and the currents? Do we have to expect larger diameters in cable connections to charge the car?
I mean, yeah, I mean, in the DC side of things, of course, there's a lot of things to double check. Of course, if we go from, but it's going to depend in the end of what's the DC voltage that we use for the DC bus. That's still to be, yeah. I mean, in this, the conceptual work we did in this work was to propose a conceptual architecture, but the thickness of the cables is going to purely depend on what voltage we decide is this bus to be.
Okay, I just talk from some experience.
Mm-hmm.
If I go to a charger, a fast charging system, what's 150 kilowatts, then I really have to carry a thick cable to my car to charge the car. So when I need this wiring, kind of wiring in my house, it's something.
Yeah, definitely.
Okay, that
I mean,
generated my question.
Mm-hmm. Yeah, but I mean, I don't see that fast charging is such an important need in a residential setting. I would say that here the benefits come from the efficiency gains from having a DC connected. I mean, then we can go through the panel directly to DC, directly to the car, and we don't need to do additional conversion steps.
That's very, very smart. But anyway, it has to fit what the storage unit is designed for. Normally you have your solar panels, your inverter, and if you go into your storage unit, then in some kind you have to have the DC level to the storage unit and to the car, which need somewhere maybe some DC-DC link to work efficient.
Yeah, no, we fully agree. Yeah.
Okay. The next question coming up. It's addressed to Littelfuse. How does the thermal performance of SMPD-based designs compares with non-isolated discrete designs?
Yeah, a good question. So the thing is, SMPD being an integrated isolated package as compared to the standard discrete with external isolation foil, one might can think of getting a benefit out of it by reducing the thermal resistance or improving the thermal performance as well as the power density. But to quantify this, we really did an experiment because that was actually a question as well for us that, okay, what is the quantification if we say this? So what we did was we take 25 milliohm silicon carbide chip, we package it into the TO247 standard discrete, then we package it into the SMPD with alumina ceramic, and then we pack it to the SMPD with high performance ceramic. And then you run the thermal measurement all across the devices. So the chips are same, the packages are different. The thing is, in case of TO247, the industry standard approach is to use some external isolation method in order to isolate the heatsink of the mounting plate. So in that case, in our case as well, we did the same method. We took different thermal conductivity of the isolation foil, going up to as high as 6.5 watt per meter Kelvin. And then we run this experiment at 40 amps to achieve something like 130 degree of junction temperature all across the device. And there, what we saw was really fascinating. The result of SMPD was such that as compared to the standard discrete with external isolation method, the SMPD chip inside the SMPD was 75 degrees Celsius cooler, 56% reduction in terms of thermal resistance junction to heatsink, and also to that all across the board like 40 ampere same current. And these measurement results are there on figure number 3. Yeah, on the article figure number 3. And they are the detailed results with different kind of experiment performed and what were the results out of it. So those were really fascinating results for us.
Thank you, Aalok.
Hello, this is Simon from Infineon. Aalok, I have a question. You introduced the SMPD product. So I wonder, this is this module is mounted on PCB. How to managing to each module and can heat to the using the same heatsink? I wonder.
Right.
For example, yes. Yeah. Okay.
Yeah, I understand your question. It's a good question. So look, SMPD is a top side cooled package. So the thing is, like for example, I'm just giving an example. This is the package what I have. Imagine this a heatsink, right? So you put this package on the heatsink, and your PCB will come like this. Do you understand? So you don't need to use those discrete heatsink all across the PCB what you have in the conventional way. You can use actually a big heatsink block, which can be a chassis itself of the device, of the application. Say for example, solar inverter, right? So you have that metal chassis as a heatsink. Use that, you mount your device because it is anyway isolated, no harm on it. And this will be mounted on the PCB like this. So it is sandwiched between the PCB and the heatsink.
Ah, okay. So you're not heavy is a general heatsink using the chassis and the very thin because this is very good some what kind of low loss. That's why not heavy heat sink like the big heavy.
So this is another very good aspect or question you have raised. As I said, when your chip is cooler, then automatically my thermal efforts are reducing. So I don't need that copper mass, you know, to get the heat out of it. So that's you are right that it really reduces the amount of heat sinking, or you can say simplification of thermal design, I would say.
Okay, thank you. Explanation.
Yeah, most welcome. Most welcome.
Thank you. We are ready to go to the next question. It's addressed to Navitas of the future. What's your visibility on future and emerging applications? It's a little bit magic.
Sure. So, yeah, emerging applications. I think I described a couple before, but we see solar going to the higher bus voltage for higher power applications. That's a trend we're seeing right now. Obviously, I mentioned all the EV moving to 800-volt buses. There's a discussion of battery voltages going to higher bus voltages. Obviously, heavy duty 1,000 volts, but for you know, passenger cars to go even higher. But I think that's still a few years out. For 3.3, we see, for 3.3 kV, we see medical, MRI, X-ray, these pulse generated power supplies. That's something which is taking off very quickly, especially for silicon carbide. There's a transition from, you know, traditional silicon to silicon carbide. Now we see that. And obviously for the higher voltage, for 6.5 kV, you're seeing the traction, but also auxiliary power supplies on locomotives and trains. We see right now today people use 1500 volt silicon MOSFETs, and we see that move to now higher voltage silicon carbide MOSFETs. You know, just 1 ohm, very lower power. You know, below 200 watts. There's a big trend on that. Yeah, there's another thing, data centers. Obviously, data centers are using, you know, PFC diodes. There's the trend to move towards the MOSFETs. There's another trend for this OCP, Open Communication Project, which is going to higher voltages for data centers. So, and that'll be requiring 1200 volt MOSFETs. So we see this happening too. Yeah, I think that's the main ones.
Thank you, Llew. The next question. So now I got the right one for Littelfuse. Is there any work about to make SMPD a standard for the market, allowing a real second source? Now I got the right questions.
Yeah, right. Yeah, it's a good question. Question once again from our audience. So the thing is, as I mentioned, in like the SMPD was pioneered by Littelfuse since 2008, but very recently we have our you know, colleagues in our industry, major competitor, who is actually offering the SMPD-like package, so-called SMIT. And that's good because it's a second source, you know, availability now, which really solves sometimes the problem for the customer asking for the second source availability.
Thank you, Aalok. So let's see what will be our next question. What else are you planning to address with these transfer molded modules? It's addressed to Rohm.
Thank you. Yes, I mean, I already spoke a bit about this, but yes, we are planning to make these modules AQG 324 compliant, so and to make them for available for both for industrial, I mean for automotive applications, but also we are targeting industrial applications in general. That's the first step. So PV applications, data centers, so UPS systems, and then move on to onboard chargers and so on until we get to automotive in general. But that we are considering this broad approach to how to implement the same dies we're offering in our discrete lineup, but now in a 6-to-1 or a 4-in-1 package. So in the end of more or less all the applications we're tackling with discrete devices that can be tackled one or two, or can also be addressed with this new package. Furthermore, the DOT can use, I mean, as you can see in the article, presents RDS(on) values that are lower than our standard portfolio. But we are also extending continuously our portfolio as well in discrete devices. This is also going to be observed in the future.
Thank you, Carlos. A question addressed to Littelfuse. Here we go. How much can the thermal performance of SMPD be further enhanced by using high-performance ceramics?
Yeah, I can answer this. So the keyword is high-performance ceramic-based SMPD. So the thing is, conventionally across the industry, if you see, then the isolated packages are usually offered with the alumina ceramic inside conventionally by far. Now, one drawback of the alumina ceramic is that you compromise on current density and power density of a packaged device. So chip may withstand more current, but because of the reduction and because of this barrier of ceramic, you reduce the current and power density of the whole package. Now, with the advent of wide band gap is an expensive material. So this compromise on the current and power might become unacceptable in the application. So to solve this challenge, Littelfuse has developed a high-performance ceramic-based SMPD, which has, as the name suggests, there is a high-performance ceramic inside, and especially for the technology like silicon carbide, which is expensive, this will give a lot of value addition to our customers looking at the thermal performance out of it. And to put some numbers into the perspectives, I discussed few numbers, maybe I can discuss a little bit more. If you compare the performance of high performance ceramic SMPD on one side, on the other side, a standard discrete with external isolation method, then as I mentioned, 75-degree reduction in junction temperature. We saw 56% reduction in R theta junction to heat sink, 58% reduction in temperature swing between the junction and the heat sink. So you can imagine the multiplying effect or amplifying effect on the reliability and the device lifetime point of view. And that's how the high performance ceramic SMPD benefits in the system in reality.
Thank you, Aalok.
No problem.
Any question at that point? Now we have another Littelfuse question. Okay, it is, what's the added value of the SMPD in power converter designs? Goes again to Aalok.
Yeah, I can take this. So apart from the advantages discussed so far in terms of thermal performance, etc., there is a real advantage in terms of two aspects. Another two advantages. One is application power output increase. The second is the system level cost saving. If you talk about the first one, let's say application power output increase in the converter design or any application, for example. Now, as theoretical, just very thumb rule estimation, if we take from our measurements what is mentioned in the article, the SMPD with high performance ceramic could handle up to 28%, or in absolute terms 11 ampere higher current for the same junction temperature as compared to the standard discrete setup. So if you imagine 800 volt DC link for 1200 volt device multiplied by 11, very rough thumb, very simple calculation suggest direct power output increase by, I would say, more than 5 kilowatt in this case. So this is one aspect. The second aspect is a cost aspect from the system point of view. Now look, the SMPD itself being an isolated package, there will be certainly a markup for this isolation offering as compared to the standard discrete two devices if you compare. Now, in this case, if you look at the system level, then the picture gets really interesting. So in case of, let's say, 22 kilowatt active front-end converter, if you design it with 25 milliohm discrete packages, you might need to end up 12 discrete. In case of high performance SMPD, it will be just 3 components. So you are basically saving the SiC content, which is expensive. So the first overall system level aspect, cost saving. The second is isolation foil. No need for SMPD because it is isolated package. The third, consider the mounting efforts. So in case of standard discrete, you need what? Discrete heatsink, you need screw, washer, you need a manpower which is specific or specialized, who can mount the isolation foil properly, quality checks in the production, and so on, for example. For SMPD, as Mr. Bodo mentioned earlier, more or less automation-friendly package, pick and place, volume production, achieve the economy of scale during the application, PCB production, and so on. And the SMPD, since, as I said, automation-friendly setup, no isolation foil, all these reduces the overall cost of a system. And one more thing is, you don't have isolation foil. That means the warranty claims, which might be associated over the period of time in the discrete design, might reduced or maybe vanished. So looking at this wholesome picture, that's how SMPD offers thermal performance, system level cost saving, and most importantly, power output increase of an application.
Thank you, Aalok. I got a finally question here from the auditorium addressed to Infineon. What's Infineon doing about equivalent SMPD devices?
Okay, I think I can also take this question. We have not announced it, but we already have similar idea used for other class of power devices, namely low voltage MOSFET, and that is what we call the topside cooling surface mount power device. And unlike the SMPD, the device that Infineon launching is non-isolated. So that means the mounting approach will be different. So some form of isolation will be required. And also another important point that I recall a question from the floor before that, what need to be done to make this SMD power devices industry standard to facilitate second sourcing. The solution is that a package from Infineon has already obtained the industry standard. So I'm recalling the name of that standard. So that means that package is already available for the whole industry to use. So therefore, that will facilitate the customer to find second sourcing. So, and also as usual, first is a package development, and then it's later to put the right chip into the package. So therefore, first we have the 600 device, silicon MOSFET and silicon carbide MOSFET, And then we were also going to have 1200 silicon carbide MOSFET in the package of this topside cooling DD pack and QD pack.
Thank you. We get more questions coming. This question is addressed to Aalok.
Mhm.
How do you ensure the clearance between the heatsink and the drain pad in high voltage applications?
In case of SMPD, drain pad like you have in standard discrete does not exist, because if you imagine a standard discrete, for example, I have in my hand, like this, right? So at that time, you have this pad as a drain pad or drain potential. But as I mentioned, SMPD is an isolated device. However, if you are asking how do you manage the distance between the pin and the heatsink, then I would like to tell that the clearance distance is 4 millimeter. So there are certain applications where definitely you need some kind of measures to manage this clearance distance. And also, if you talk about creepage, then it is, I think, more than 5.2 or something in the direction of 5.2 millimeter, which is by far helping such voltage class of an application.
Thank you, Aalok. Gentlemen, thank you. It was my pleasure. I have to apologize that we have had some little technical problems flashing in the questions. Maybe it was only on my side, but it was always a fruitful and good session that we had, and it benefits for all the people who are reading the magazine and want to have additional information for their application work. I hope you have a nice day wherever you are located, and I will say see you soon again, and I will say goodbye, gentlemen and friends.
Thank you very much.
Thanks,
Bye.
Bodo.
Thank you.
Bye,
Bye.
gentlemen.
Good day. Have a good time.